Now we will introduce methods for determining whether a correlation or relationship between two variables exists. Specifically, we'll be testing to see if there is a linear correlation between the two variables. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. In the problems in this section, we'll be working with paired data, x and y pairs. Creating a scatter plot of the data is a good way to begin the analysis, as it provides a visual representation. So let's look at some examples of some scatter plots. Okay, in this scatter plot, what we would say that we're noticing here is as x is increasing, going from, of course, here at the origin 0, in the positive direction, x is increasing, we see that for each data point our y is increasing. X goes up, y goes up. We go out here to x, and now y has gone up higher, out here to x, and even higher. So we see what we call a positive correlation between x and y. So let's make a note of that. This would be what we call a positive correlation between our two variables, x and y. And so we would say as x increases, we might make a note like this, as x goes up, y goes up. And likewise, as our x decreases, as we go this way on the x-axis, our y's are going down. Okay, let's look at another example. Plot these points, and now what we see, as x increases, our y's are dropping. As we get out to these x's, y is getting closer and closer to 0. In our early values of x here, the y's were higher. So here what we see is a negative correlation. Between our two variables x and y. So in this case, as our x increases, our y is decreasing. Now you might recall when you learned about slopes of lines in an algebra course, that lines that rose from left to right, that went uphill from left to right, we called that that was a positive slope. All those lines had a positive slope if they went uphill left to right. Likewise, the lines that went downhill left to right had a negative slope. So this goes along with that. We're talking about linear correlation lines, how close these points are to forming a line, and in what, if they're forming that line in a particular way. Here in a positive correlation, here in a negative correlation. So now let's look at another example. Okay, when we examine these points that have been plotted, we don't really see any correlation at all. The points are just sort of scattered about, and there doesn't appear to be any particular relationship. As our x's increase, some of our y's increase, some of them decrease, and likewise the other way. So here what we would say is there appears to be no correlation between x and y. Okay, and then finally we might find that if we plot a scatter plot, we see what we call a curvilinear relationship. There does appear to be a relationship between x and y, but not one that we would call linear. And actually this one appears to be somewhat quadratic. Remember the parabolas from your quadratic equation? But it's definitely not linear. So the types we will be looking for in this section are linear, either positive or negative correlations. And sometimes we're going to find that there is not a correlation, or it's possible there is one, but it's not linear. And that's all we're looking for. So just because we'll conclude that there is no correlation, we're talking about no linear correlation, that doesn't mean there's not a correlation, but as I said, we'll be looking for a linear correlation. Okay, so we have a correlation coefficient for the linear correlation, and the symbol we use for that is the letter R. The linear correlation coefficient R measures the strength of the linear correlation between paired quantitative x and y values in a sample. They're paired, each x is paired with a particular y, and quantitative, remember what that is, those are numbers that represent counts or measurements. That's the kind of data we're working with here. So you might have an example of some plants that were studied, and so they were exposed to a certain amount of sunlight. Well, these are measurements for x, and then for each plant the amount of sunlight is recorded, and then how tall the plant is would be the y value. So for each amount of sunlight there would be a paired y, that is the height of the plant. And then we want to see, well, how strong is this relationship? If it appears to be a positive correlation, say the more sunlight you give the plant, the taller the plant grows. As x goes up, y goes up. But it's probably not going to be on a perfectly straight line. So we want to find a way to talk about how strong that linear correlation is, and that's what the correlation coefficient will do. It will give us some feel for how strong this relationship is, if indeed there is one. So R is kind of like a measure of goodness of fit, how much this data that we have fits a straight line. It obviously won't all line up perfectly, but how good a fit is it to a straight line? And so that's what the R will tell us. And our R values that are closer to 1, we'll take the absolute value of R and compare that to 1. The closer they are to 1, the better the fit. So let me just make a note of that. So this absolute value of our R value, because R can be positive for a positive correlation, uphill left to right, or R could be negative for a negative correlation, downhill left to right. So we want to take the absolute value to get that positive, and then compare that. We'll compare this absolute value of R compared to the number 1. And the closer it is to 1, the better the fit. The stronger we feel this correlation is. It's our measure of the strength of the correlation. Okay, so R is calculated using our sample data, our XY sample data, so it's a sample statistic. And when we have a sample statistic such as X bar, recall that we have a population parameter, and that is rho. It kind of looks like a funny looking P. It's a Greek letter rho, and this is our population parameter. So recall in the past we said that we can use the sample mean to estimate our population mean, mu. We can use our sample, remember our unbiased estimators, our sample variance to measure the population variance, sigma squared, the sample proportion to estimate our population proportion P, and now we have a correlation coefficient R used to say something about or estimate the population correlation coefficient rho. So it was just in this same vein that we're talking about this new statistic and its population parameter.